We need to unmute him, is it?
You need to do, sir.
Okay.
Not there, but then it contains a lot of other information.
So just one minute. There's some background noise. Yeah, please go ahead, Mr. Sriram. Yeah, NPTEL, can you just check this whether we need to unmute or
No, sir, he can only
okay,
unmute.
but he's not doing it.
Maybe some mic problem, I think, sir. Sriram, you
So
can post
everything.
your question in chat.
Yeah, you can also put the question in the chat if you want. Yeah, hello.
Yes, sir.
Oh, he is also there.
He left, sir.
Okay. Let's just wait for 5 minutes and see.
Okay, sir.
Good afternoon, sir.
Geography.
Sir, I have a question. That does conduction occurs in gas phase?
Yes.
Because all the atoms are in random motion.
Yes. Yeah.
So
So even in gas phase, if you have a temperature gradient, right, then if you take a surface through the gas across which there is a temperature gradient, right, the molecules crossing from below to above will have, a lower temperature, and the molecules crossing from above to below will have a higher temperature. So,
yes, sir.
so if there is a temperature gradient, there will be a flux across. Okay, simply because molecules crossing a surface are coming from a distance comparable to the mean free path above the surface.
Yes, sir. So, but they are in motion, so they it can be taken as conduction or convection more of the type.
Okay, so transport due to molecular fluctuating velocities is conduction. Okay, transport due to fluid velocity is convection.
Yes, sir.
So even in a gas that is not that is stationary, right, you will have
Yes, sir.
molecular fluctuating velocities. Okay,
Yes, sir.
so convection is only due to fluid flow. Okay, so even when there is no fluid motion, that is the average center of mass of the fluid is not moving, right?
Yes, sir.
You could still have molecular motion,
Yes, sir.
and that molecular motion is given by equipartition, and that will
Yes, sir.
result in conduction.
Yes, sir.
So conduction in the case of gases, the conduction is the same as thermal diffusion.
Yes, sir.
Okay, uh, whereas in solids it is not. Okay, so in solids the mechanism is different, but if you have gases or liquids, the thermal conduction is the same as thermal diffusion.
Yes, sir. Sir,
And,
there was another point in the lectures like the non-dimension flux, like
yeah,
Nusselt numbers, and
yeah.
how can means I didn't get that point so that much. Can you
So yeah.
elaborate a bit? Yes, sir.
So these dimensionless numbers are for the average flux. Right? So if you have some heat transfer from a heat exchanger, the Nusselt number will be for the average heat transfer rate or the average flux across the wall of the heat exchanger, right?
Yes, sir.
So the average flux is the average over the flux at each point on the surface, right?
Yes, sir.
So at each point in the surface, the conduction follows the Fourier's law of heat conduction,
Yes, sir.
right? For the local temperature difference and the local heat flux, right? So that is the heat flux is equal to minus k delta T by whatever the thickness,
Yes, sir.
right? But when you integrate it over, the total heat flux is not the total temperature difference divided by the total thickness, right?
Yes, sir.
So you have to integrate the heat transfer rate at each location, right?
Yes, sir.
So, but still, you're getting an average flux out, the total heat transfer rate divided by the total area, right? And from Fourier's law, that has to have the same dimension as K delta T by L. Right?
Yes, sir.
So if I divide that average heat transfer rate by K delta T divided by some length scale, that will still be dimensionless.
Yes.
So that is the reason you define it that way. In the case of shell and tube heat exchanger, the dimension will be the pipe diameter. Okay.
Yes, sir.
So you're
Sir,
dividing it by a quantity that has the same dimension as the heat flux, which is the right side of Fourier's law.
and sir, another question. In my mass transfer course, I have learned that Fick's law is been applicable for dilute systems. So when the systems are concentrated, what is the
Yeah.
uh, methods we apply out there?
So there you have to take the gradient of the chemical potential, okay, because the
Yes, sir.
chemical potential is the driving force, not the concentration itself.
Yes, sir.
So you have
So
to
we
define,
will
yeah,
go through
yeah,
activity coefficients and all.
activity coefficient and so on. So you have to define the chemical potential and the activity coefficient in terms of the concentration, and then use that for concentrating.
And so
So
what's the range where we use this Fick's law? Means
okay,
I
yeah, I mean, uh, I mean, if you use a linear approximation, that is the activity coefficient is basically 1, right? The error that you're going to be making is proportional to the concentration, right?
yes, sir.
So if you want a more accurate result, then the range for which you can use it is smaller. If you want a less accurate result, you can use it over a larger range.
So basically we will apply it to the Henry's
Yes, yes.
range,
The Henry's
Henry's
range,
law
yes.
range.
Yes. In general, for the Henry's law range, yes.
Yes, sir.
Yeah.
Thank you, sir.
Yeah. Okay.
That's
Good.
what one from
Okay.
my side.
Okay. Thanks. Okay. So there's no one else, right? Hello.
No, no, sir.
Yeah. Okay. So we can close it now.
Yes, sir.
Yeah. Okay. Thank you.